Hi, good morning, everybody. My talk today is called Metal with Training Wheels. So I just kind of give a little bit of a background about myself and why I'm giving this talk and how I got from where I was to where I am right now. So back when I was going to college, I didn't go to college for computer science. I was really interested in doing things that were artistic, and I wanted to make movies and tell stories and do other stuff. So I went to school for journalism because my college did not have a film school. And I got out of college, I really couldn't figure out anything to do with my journalism degree, so I kind of doubled down on it. I went to school for video editing and audio engineering. And shortly after I finished my audio engineering degree, the Great Recession hit, the economy collapsed, and all of the places that I thought I was going to work at after I got out of college, they all went out of business, or they laid off half their people, or they just kind of stopped existing. So at a certain point I was like, okay, you know what, like I've got to be, I've got to grow up now. I'm in my late 20s. I've got to actually do something that's practical. And so I was either going to go to law school or I was going to go into computer programming. Law school was $100,000 for 3 years, and programming was 2 years, and it would cost $100 a credit at the local community college. So doing the math, I was like, okay, you know what, this seems like it's a better gig. So I went to community college and started learning about programming, and that was around the time that the iPhone had come out and was getting to be really, really hot and really big. And while I was taking iOS classes, I found out about Core Audio and OpenGL and like Core Animation and all of the different media frameworks associated with iOS. And I got really excited because I'd spent all of these years working with all of these programs, and to find out that I could actually go in and write these programs in code and create my own Photoshop or create my own Pro Tools, like this blew my mind. I thought that this was like the most amazing thing ever. And like I felt like mentally awake for the first time in years, and this got me really excited about programming. So a year after I had finished all of my stuff with iOS, I learned on Objective-C, and after I'd been in the job market for about a year, Metal and Swift were both announced in 2014. I like to say that Metal was the most exciting announcement of WWDC 2014 for exactly 10 minutes. And like, I got really excited about going in and learning all of this stuff because this was the thing that I'd spent years doing, and I really wanted to have an understanding about how everything worked under the hood. So I got really excited about Metal, and I started getting into it, and I realized that Metal was very different from what I had kind of gone into it expecting it to be. So when I first got interested in Metal, I got really interested in it because I thought it was like a graphics programming framework. I was kind of thinking that Metal was going to be more along the lines of what Core Graphics wound up being, but Metal isn't really specifically a 3D graphics programming framework. It's a GPU programming framework. And what that means, to kind of change the way you think about it, is that Metal exists in order for you to be able to lay out a bunch of bits, package them up, and then send them to the GPU where they can be processed using mathematical equations on very large floating point data sets. So yeah, that's a little different from going and doing like 3D graphics stuff. And one of the advantages of Metal over something like OpenGL is that you have complete control of the pipeline, which means that you have to go in and you have to allocate memory, you have to lay it out in a certain way, you have to create data structures, and you have to set up a whole bunch of pedantic bit shifting in order to be able to get anything to go over to the GPU and then be displayed on the screen. So if you're doing rendering for graphics, you have to set up this entire pipeline of stuff in order to just get a triangle up on the screen. You have to allocate memory for all of the vertices. You have to set the vertices. You have to import them from a data model. You have to put them through this entire huge set of stuff in order to get it through this rendering pipeline in order to get something out on the screen. And like, I kind of came into this, and like, I didn't get into graphics programming and programming in general to do all of this weird pedantic bit shifting that was very boilerplate, because like I don't care enough about it to go in and try to like squeeze every like microsecond of productivity out of my rendering pipeline. I want to go and make cool stuff. I'm not necessarily interested in getting optimization. I just want to be able to do something that looks neat. So one thing that's been really great about Metal and the last couple of years with Apple is that a lot of people are like me. We don't necessarily want to go in and like know the life story of every bit that we're putting through this rendering pipeline. We want to go in and make cool stuff. So Apple has a lot of frameworks that are built on top of metal that take away a lot of this boilerplate optimization stuff so that you don't have to worry about, like, you know, laying out all of your vertices and your bits and everything in the most efficient manner possible. It'll take care of that for you, but it will allow you to dip down to the metal to work on the things that you actually are interested in caring about. A lot of people who are interested in graphics programming, like there's a program called Shader Toy that's written on WebGL where all you do is you write fragment shaders and you can do lots of cool stuff. You don't care about how, like, all of the rendering stuff gets taken care of off-site, because all you care about is figuring out what you want to do with your really cool fragment shader. And so Apple has tried to create different frameworks that allow you to have the same experience on iOS. And I'm going to talk briefly about a lot of these frameworks today to give you an idea about what you can do if you want to take advantage of metal, but you don't want to have to be responsible for the entire rendering pipeline that you're setting up for your graphics. So, like, I had this up here before where I showed, like, this giant, like, rendering pipeline. Now, if you use something like SceneKit, you don't have to worry about packaging all of your bits and doing all of this pedantic stuff. All you have to worry about are your vertex function and your fragment function, which are honestly like the fun, cool, creative parts of working with GPU programming. Again, there are several advantages of using higher level abstractions. Like, you don't have to learn the entire metal processing pipeline. I wrote a book on metal programming. I have one chapter on shaders, and most of the rest of the book is basically talking about how to set up all of these different rendering pipelines and how they interact with each other. And it's a lot of stuff that's kind of generic and it's not really that interesting. Wait, I'm not really doing a good job of selling you on why you should buy my book. But, like, all of the stuff that I was really interested in doing with metal was not it was kind of like the tip of the iceberg, and there was a lot of other stuff that you needed to understand in order to work with this tip. And, like, that isn't really necessary, and so if you're not interested in all of the other low-level processing stuff, you don't have to deal with it. It's easier for you to go in and learn all the stuff that you're actually interested in learning because you don't have to focus on all of these other low-level things. And me coming into metal, like, I didn't know a lot about the rendering pipeline and all of this other stuff. I just wanted to write shaders. And so, like, by abstracting things away, it's easier for you to get introduced to different concepts associated with machine learning and graphics without having to go in and learn how to set everything up from scratch. And they'll let you get things done more quickly because you don't have to worry about setting up a bunch of boilerplate just to get a triangle to appear on the screen. So I've talked a little bit about metal being a GPU programming framework, and I want to kind of get into how all of these frameworks and how metal even works within the iOS ecosystem. So kind of the process of what you're doing with metal is that you're packaging up a bunch of bits and you're sending them to the GPU. And shaders are short programs that are written in a C++ language called the metal shading language that has a lot of math-specific features in it that aren't available in C++. So if you're familiar with something like the OpenGL shading language, they're almost directly mappable, where you can almost completely just copy and paste from an OpenGL shader over to a metal shader. So over on the CPU, you're taking your vertices, your texture data, your neural network weights, you're taking all of these things and you're packaging them up into a giant, like, thing of bits. And then you're sending that to the GPU. When the GPU gets that, it knows that it's gotten this giant package of bits, but it doesn't really know what those bits are. It knows there's like 120 bits of data in here, but they don't know what that correlates to. So on the GPU side, within your shaders, you need to create a data structure that decodes for the GPU what all of these different bits correlate to. So it knows the first 16 bits are like color data, and the next 16 bits are your vertex data, so that it can go in and take the specific bits that it needs to and apply the mathematical processing that you want it to. And I've got some examples where I'll show that, so it's a little bit less abstract. So, like, just in an example, if you were doing a 3D graphics rendering program and you had a light source and you had a cube, you would need to be able to convey to the GPU, like the angle of the light source, how intense the light source was. You'd have to convey all of the different points on the cube. You would need to be able to tell them like how to reassemble the cube. And these are all pieces of information, and any color data or texture data associated with the cube. So these are all pieces of information that you need to package together to send over to the GPU. And if you're doing this in Metal, you have to go in and you have to create all of this stuff from scratch. You have to allocate your memory, you'd import like an object file, and you'd have to go in and encode all of the data into a data structure in order to be able to get it to the GPU. So these higher level abstraction frameworks will go in and they'll know the types of information that the GPU needs in order to do common processing on it, and it will create their own data structures that are easy for you to connect to so that you don't have to worry about doing all of this manually. So, yep, basically just said all that stuff. The first abstracted framework that I'd like to talk about is SceneKit. When a lot of people think about like 3D graphics programming in iOS, like they think that they have to drop down to like OpenGL or Metal, but SceneKit's actually a really good abstraction on top of 3D graphics that I don't feel gets as much attention as it could, and that kind of disappoints me because it's a really neat framework. So there are a couple of different ways that you can drop down to Metal from SceneKit. The easiest one is snippet injection. So there are a couple of different points in the process, the fragment process, the vertex process, the lighting, or the geometry processes, where you can just go in and create like a couple of lines of Metal code and you can just inject it into the fragment shader. So like one easy example I've had of this is if you wanted to just output everything being red, you could just inject a snippet that sets the output of the fragment shader to red. It's one line of code, it lets you drop down to the Metal, and it's a way of being able to do really easy, small changes to the rendering pipeline without having to set up an entire shader. The next way that you can do that is to completely replace the programmable rendering pipeline by creating your own vertex and fragment shaders. And that uses the SCN program object. That means that you're not getting anything from SceneKit. So if you created like a light inside of SceneKit, all of that information is getting thrown out, and you're responsible for creating your own information within the programmable pipeline. And then if you wanted to do something that was a lot more intense, that required multi-pass rendering for like deferred lighting, blurs, and other stuff, there's another even more further abstracted framework called SCN Technique that allows you to do multi-pass rendering in SceneKit. And again, like when I was talking earlier about the cube and the lighting and so forth, there are certain things that SceneKit knows you need to have in order to write your shaders. Like some of that is the model view projection matrix, the lighting position, the vertices, all of the different geometries and textures associated with your objects. And because it knows that those are generally things that you need in order to write shaders, they're all packaged up inside of data structures that are that you can look at in the documentation. So when you have an equation that you want to translate over to a shader, you just look for whatever it is that you need and then check against the documentation to figure out how to access it from SceneKit. And like at this point, it isn't necessarily important for you to know like what the model view projection matrix is. All you need to know is that it's something that you are being asked to include in your shader, and that SceneKit will give it to you, and so you can just use it and you don't have to worry about what it is or how it actually works, which is nice when you're just starting off and you're learning and you don't really have any familiarity with what a lot of these weird phrases actually mean. So again, it's a good way of learning how to do stuff by having access to things that allow you to get things done without having to know everything about graphics programming. SceneKit has two built-in buffers that contain all of the data you need to access in the geometry. The first one's the frame buffer, and that includes the current information about the world and object space data associated with your objects. And then the second one is the node buffer, and this includes information like positions, normals, texture positions, etc. So within your application, you need to create data structures that talk about like which of these information from SceneKit you need access to in order to write your shader. So in this one specific example, I needed the model transform, the model view transform, and et cetera. And so I created my data structure in my shader associated with what I need from the node buffer. And then the input that I need for the vertex for this one was just the position in the normal. And they had the SCN vertex semantics position, semantic normal. Again, there's a large list of things that you commonly need to have access to in order to perform 3D graphic shaders. And then you pass these in as parameters to the vertex shader. So again, like the biggest win that I see most people getting with doing higher level abstractions is generally in SceneKit, but SceneKit's not the only framework that Apple has that allows you to do shader work. Another one is SpriteKit. SpriteKit is their 2D games framework. And SpriteKit's set up a little bit differently than SceneKit was. So with SpriteKit, you have an SK shader class, and then you have to set up your uniform variables rather than bringing them in the way that you did with SceneKit, because SceneKit was a little bit different because it had to deal with the a lot of transforms and so forth in three-dimensional space. And SpriteKit's more of like just a texture modification. So you saw before that we had to create like a custom data structure on the GPU side to decode the information that we were getting from, sorry, there was a little bit of, we had to set up a custom data structure. You don't really have to do that in the same way with the SK shader class. You can just create uniforms and you can encode them using this uniforms array. The other area where I think that there are wins with working from a higher level abstraction is with core image. So if you wanted to go in and do image processing, you can use core image to create custom metal kernels to do image processing. So back when iOS first came out, core image was something that was only available on the Mac. Eventually it was brought over to iOS, but up until iOS 11, like you couldn't actually write metal shaders for core image. You had this weird like core image kernel language that you had to learn in order to do kernel shaders for iOS. So before I was kind of talking a little bit about how you had vertex and fragment shaders. You use those when you're doing a rendering pipeline. Core image technically uses the compute pipeline, which means that you only have to write one shader, which is the kernel shader. So like going and setting up image processing in core image is much less of a hassle than going and setting up a rendering pipeline in either like SpriteKit or SceneKit. And again, it's very simple. You go and you write your kernel function that talks about how you want to process your image, and then all you need to do is you initialize it with the function name coming from the Metal library data. So there's a lot less setup that needs to go into using Metal with core image. A lot of that is abstracted away and taken care of you, and it's really easy to take advantage of Metal using core image. One of the big wins that we had with Metal over OpenGL was that Metal allowed you to use general purpose GPU programming, which meant that it didn't have to be used in a rendering pipeline for 3D graphics or for things that were specifically graphics related. You could go and you could work on any large data set and you could apply math to any large data set. So there are a lot of structures within Metal, they're adding a lot more every single year associated with doing things like neural networks and going low level and allowing you to do a lot of machine learning and machine vision processing on the iPhone, and that was a big focus of WWDC this year. So one of the nice things that they're doing is they're trying to create higher level abstracted frameworks to allow you to take advantage of the general purpose GPU programming without having to understand how to set up a neural network. You can go in and you can take a trained data model and you can bring it into Metal and you can use it in your project without having to understand how the neural network GPU stuff is working under the hood. But unfortunately, kind of the way that the compute pipeline is set up, I mentioned with core image that there was a lot less setup that you needed to do for core image because you were using the compute pipeline and not the rendering pipeline, which means that with these higher abstracted frameworks for the machine learning with like the Create ML and Core ML, that basically like if you want to drop lower level than that, you kind of can't take advantage of them anymore. If you want to do anything that's in any way specific and customized, you still have to go all the way down to the Metal and kind of stop using Core ML or Create ML. But like fortunately, the compute pipeline is a lot less complicated than the rendering pipeline is, so even if you do have to drop all the way to the metal to implement your custom neural networks and machine vision stuff, it's still a lot easier than going in and setting up an entire rendering pipeline for 3D graphics. So it's great that we have these higher abstracted frameworks that are written on top of the metal performance shaders that make it easier to go in and use machine learning without having to understand how all of the stuff works under the hood. But again, if you're not doing something that's custom that's going to work directly with the way that Apple expects you to, you're gonna have to create your own custom stuff. But again, it's not that hard. Okay, already talked about that. So in the spirit of this being an Apple Developer Conference, I felt like we couldn't really get through it without having the just one more thing. So I've talked a little bit about a lot of common use cases that people have had with needing metal for custom graphics and machine vision stuff, but there's been one case that Apple has not actually addressed very well, and that is going and processing live video streaming. So if you want to go and process live video streaming, you have to jump into AV Foundation, which is a real pain in the butt. You have to set up a whole bunch of stuff. You have to capture an image data from AV Foundation, send it to Metal, process it, and then send it back. And this is a lot of boilerplate code, and a lot of it is really complicated, and like you don't really need to do anything custom with this, so it's just boilerplate that you have to do over and over and over again. And back in 2012, there was a framework that was released that wrapped live video image processing to make it easier for people to integrate it into their applications. And that third-party framework was GPU Image. So that one came out in 2012, and that was doing pretty well for a couple of years. Then in 2014, Apple introduced both Swift and Metal. And a lot of people, after a couple of years, they didn't really want to be working with all of these old legacy Objective-C frameworks. And after a couple of years, the creator of GPU Image figured there were a lot of architectural wins that he could get from converting GPU Image from Objective-C to Swift, one of which was actually being able to run it on a Raspberry Pi. And so back in 2016, GPU Image 2 was announced. So now, a couple of weeks ago, we had WWDC. One of the announcements that they made during the Developer State of the Union was that Apple is in the process of deprecating OpenGL. So GPU Image was still written in OpenGL because we wanted to make it cross-platform, wanted to make it available on Linux, wanted to make it as widely available as possible and go back as far as possible. But now that's not really going to work out any longer because OpenGL is no longer going to be supported by Apple. So I am announcing the creation of GPU Image 3, now with Metal. So we're in the process of porting the framework over. Right now we have the ability to do live video processing on both Mac and iOS. I personally, before I came out here, ported a dozen or so shaders that were dealing with color modification. So those are kind of like the easier ones. I'm hoping in the next couple of weeks to get all of the rest of the nearly 200 shaders brought over from OpenGL. And the original creator, Brad Larson's been working on trying to implement as much of this as he could before I was able to come out here and present this. So as of right now, I'll be taking over Brad's role as the curator and maintainer of GPU Image. And this link went live earlier today, so it's available to use right now. All of the architecture is set up in such a way that you should be able to just take and change your module from GPU Image 2 to GPU Image 3, and everything should just work. Because it's an Apple product and it all just works. So I'm really excited about this project. I'm hoping that people who are a little bit intimidated by Metal and don't have a lot of experience with seeing how an actual project works will be able to take this and learn from it. And I'm planning to write a series of blog posts about how all of the math inside the shaders works so that people can come in and learn a little bit more about the shading language and have a little bit easier time of being able to come in and learn a bit about Metal, because I think Metal is a really important technology and I really would like people to be as excited about it as I am. So, Takeaways, higher level abstractions are your friends. Anything that you can do with Metal, like 3D graphics, 2D graphics, live video streaming, machine learning, all of this stuff has some kind of higher level abstraction available that allows you to go in and take advantage of Metal without having to know how to do all of the pedantic bit shifting and memory management and curation that you don't necessarily want to have to deal with when you're first learning and starting out with GPU programming. So that is what I have. I'm happy to take questions, and I hope that this was somewhat informative for you who may not have worked with Metal to figure out how the easiest way is for you to get in with that. So thank you. Questions? Comments? Hey. I'm trying to think about that because, like, okay, yeah.
Are there specific rendering tasks that are more performant on CPU than GPU?
If you're working with smaller data sets, then it's usually more performant to work on CPU rather than GPU. So, like the Accelerate framework, if you're working on like data sets of less than like 10,000 like numbers, generally, it's faster to set things up in Accelerate, but like if you're working with really small data sets, even setting things up in Accelerate is usually not as quick. And then like Accelerate will do a lot of the same things that Metal does. It's done on the CPU rather than the GPU. So that was a good question. Yep.
So I was playing around with some of Apple's examples in the graphics pipeline, and even as recently as last year, it seems like a lot of their hand-coded some really common operations like transformation matrices and things like that, or else they actually did some of the old OpenGL helper code to do that same thing. And that's 2017 year.
Yeah.
I've heard that Apple kind of wants you to write in SceneKit or SpriteKit or something and just dip into Metal to be custom shapers.
Right. Oh, I've been told that's true. When I was working on the Metal book, I was collaborating with somebody who was at Apple but isn't at Apple any longer, and I said to him, like why should people set up like all this stuff in Metal when you could just do it in SceneKit? He's like, we want people to do things in SceneKit. Like they do want everybody to start off in SceneKit and try to get as much done in SceneKit and only drop down if you encounter something that you physically can't do in SceneKit. So no, that is their intention, and like I really wish that they would push SceneKit a little bit more than they have, because like I talk to people and I think more people know about Metal than know about SceneKit. And so it's kind of disappointing because like I said, SceneKit's a really powerful, neat framework and it really allows you to do a lot of stuff, and I really highly recommend people use SceneKit. Yep.
Is there much difference between Metal on Mac, iOS, and Apple TV?
There isn't a lot, like there's less different between like Metal and than there was with OpenGL, because with OpenGL, like you had to do OpenGL straight on the Mac, and then you had to do OpenGL ES, and even though they were very similar, like you still had to do a lot of different stuff. Like right now, I think with our port, we'll have like half as much code because we don't have to set up separate like Metal views for the Mac and for iOS. They like everything just kind of overlaps the same way. So
What is the difference though?
I don't think there's much of a difference. I haven't worked as much with the Mac. I've primarily worked with iOS, but like my understanding was that like the MK view, like the Metal view in MetalKit, like if you're creating one, it works on both Mac and iOS, and that you don't have to make changes based on which platform you're on. Don't quote me on that though.
Is there an easy way to convert the shader toy shaders into something that Metal can use?
So I believe that the shader toy shaders are written in the OpenGL shading language, and again, like I said earlier in the talk, like they're almost directly mappable to OpenGL. Like there's a couple of semantic change differences. So like if you have like a vector of 3 things in like GLSL, it's called a vec3, but then in Metal, it's called a float 3 or a double 3 or whatever it is that you're doing. So you just have to kind of change the data types from whatever the GLSL is to Metal, but like it's almost like you can almost copy and paste most code from like shader toy fragment shaders over to a Metal shader.
Just as long as it doesn't use a specific library or something.
Well, the library was designed to basically overlap with GLSL, so like all of the different like operations for like dot product and transforms and normalization and all the other stuff. All that stuff also exists within the metal shading language, because like it was designed to do these specific graphics mathematical functions. So like they're similar.
Essentially the same shader language.
Yeah, it's basically the same shader language. So like you might have to like change one or two things, but like you can almost again, like you'd almost copy and paste like most of the mathematical logic from shader toy over to metal. It's just setting up like figuring out like how you're going to set up all of your like scaffolding to actually get data from the CPU over to the GPU.
That should almost be an Xcode translation script.
Could be. Should be. File radar. Do we have other questions? Yep.
How's the tool support for working with metal these days? Like debuggers?
Tooling for metal is fantastic. There's frame debuggers, there's graph debuggers, like there's a whole like talk that they did at DubDub this year showing how all of the different debugging tools that they introduced just this year, and there have been tools been introduced over the last couple of years. Like debugging on metal is fantastic. Anybody else? Are we good? All right.
Yeah. So you say GLSL and MSL are kind of the same. Have they fixed any of the kind of annoying parts of GLSL, or are they carried that forward over as well?
They didn't. I don't think they didn't exactly. I think that the design of the metal shading language was kind of informed by GLSL because there's just certain things that you need to be able to do if you have like a shading language. But like I don't like my understanding, like especially with metal, was that they weren't trying to like directly port OpenGL or the shading language over to metal, because like I spent years trying to learn OpenGL and I found OpenGL just be incomprehensible. And then like I went in to learn metal and like there were no books, there were no tutorials, there's like nothing available for metal when I wrote my book. But like it was so much easier to learn metal because it was just such a simpler framework and API to learn than OpenGL was. Like when I was at DubDub this year and I talked to the metal engineers and I said, hey, I'm gonna be porting all of these legacy OpenGL projects over to metal. How much of the OpenGL should I keep? And they said, nothing. Throw it all out. If you don't know OpenGL and you're not planning to maintain it, throw it all out, start all over again, write it all in metal. All right, do we have any other questions? I will be around today, like Louis said. I have stickers that I can hand out. I'm happy to talk to people and answer any questions that you have. Thank you very much.